All right, so it's recording. This is going to be the quiz 7 review, I believe. So this will include torque, um, angular velocity, the rotational motion stuff, and then as well as like center of mass. So in this session, we're just going to do like a lecture review, going over the slides, important concepts and stuff. This should go by a little bit quicker because I feel like the presentations and the slides were a lot of examples and not so much like a lot of concept stuff, because torque is like really just force applied causing a rotation, and there's not too many like working parts, I guess, to the concept, um, and it builds upon a lot of previous knowledge. So I'll skip over the examples necessarily just because like for time's sake, and we already have a lot of examples to go over anyway. And then we'll do 3 problems as a quiz sample that I have from older quizzes, and then we'll go over any written problems that you guys have. But yeah, without further ado, we can get started. So section 1, quantifying rotation with angles. So with uniform circular motion, remember in the last chapter, not last week, but the week before, with centripetal acceleration, centripetal force, right? We had centripetal acceleration is equal to v squared over r, right? So that's your speed squared over the radius for your circle, right? Or your circular path. And then centripetal force was just equal to mass times that centripetal acceleration. And kind of a rehash of centripetal force. It's not necessarily like a new novel force on its own. It's just kind of a term or an adjective to the forces that are contributing to that circular motion or circular path that you're on. So for example, if we had like on a roller coaster, we had like normal force and gravity contributing, right? Or affecting the centripetal force, right? Those are components that help create a centripetal force, right? A force that allows you to move in a circular path. That's the concept of centripetal force. So now we have rotational motion, right? And so that's just objects spinning on an axis. Now that brings us to seemingly like an infrequently tested concept so far on the online homework and the written, which is this angular position, angular velocity stuff, and that's no more than just a rotational version of displacement, velocity, acceleration that we've been doing in like the first couple of weeks of the semester, right? So angular position is basically like the equivalent of your displacement, right? Displacement or distance, right? So we have, instead of like a certain distance over time, right? Or distance covered, we have an angle covered, right? We have theta, that's the angular position of an object or of a particle, right? So you cover a certain angle, right? That's kind of like your quote unquote distance or displacement from the x-axis, right? And so here comes the most important like notation for this entire chapter, and it applies to this and applies to torque as well. And that is, think of theta positive as counterclockwise and theta negative as clockwise, right? So if I'm looking, if you remember like from pre-calc or from calculus, if you did the unit circle stuff, right? This was like your 0 degrees, and this was your 90, right? Now, if I open this way, so this is counterclockwise, right? So counterclockwise is positive, clockwise going this way, opening downwards like this, is negative. So counterclockwise positive, clockwise is negative. That's the notation for angular position as well as for torque, which we're going to go over here in a sec. But in addition to the whole angular position concept comes a common calculator mistake, and that's using degrees instead of radians when we're doing conversions with like your angular position and your arc length. So for your delta theta here, right, that's your angular position, your change in your angle basically, that is going to be in units of radians and not degrees, right? That's how we use it, right? And the reason why is that eventually what we want to do is calculate an arc length, right? So theta is like the angle covered. L, the arc length, is actually like the distance itself covered, and that's a value of like meters, right? Or centimeters or kilometers. That's going to be your normal like displacement value that we remember from the first couple of weeks. So L is like your regular distance or displacement, right? Because remember, for distance, the equation was L divided by T, right? That was your distance. So your arc length here is your distance, and like delta theta here is kind of the rotational equivalent of that in terms of angular position being like the amount of, or like the angle that you cover total, right? So path traced by an object is an arc like this. And then that's the translational distance. And by translational, I just mean like kind of almost like a linear, just on a straight line almost, or just literally the distance that you travel without respect to any like rotation or angle or anything like that. Just solely like how far you traveled. And so like I could go 20 meters here and I covered that maybe like a 30-degree angle, right, of the circular path. So in order to convert between like your angular position and your arc length, right, we have this equation here. L is equal to R times the change in theta. And so this has to be in radians, right? So if I have, for example, remember on the unit circle, so if I covered here, up to here, this point, up to this point here, that's like 90 degrees, right? And if you remember from pre-calc, or if you took it in algebra or something, that's pi over 2 radians, right? Now, you might be thinking, okay, like, I don't remember the unit circle. How am I supposed to get these values, right? So there's an easy way. There's an easy conversion, and that is that 2 pi radians is equal to 360 degrees. So if I have a certain like degree amount, they gave me degrees, and I want to figure this arc length out, I have the radius. Now I just need to figure out what the degree is, or the angle is in radians. All I have to do is just take that 90 degrees, for example, multiply it by 2 pi radians divided by 360 degrees. So your degrees cancel out, and then you're left with radians on top, right? So 90 times 2 pi, 180 pi, right, divided by 360. 180 is exactly half of 360, so it's pi over 2, right? That makes sense. So that would be pi over 2 radians in that case. So with that, you would plug in pi over 2 radians instead of 90 degrees as your delta theta. And then if you have a radius of like 4 meters or 6 meters or something, you multiply that together, and that's how you can get your arc length. That'll be the translational distance, the actual distance in like meters or centimeters or kilometers that you cover over that specific angle, right, over that specific angular position. So this is just another example. I'm not going to go over a lot of examples from the slides because you guys are bound to like reviewed them already. But now we have something called uniform circular motion, which, remember, that's from the past week's uniform circular motion. So with uniform circular motion, we're going to talk about things in context of like these rotational values. So this is your angular velocity, right? So this is your rotational equivalent of just velocity. So velocity was displacement over time, or distance over time, right? If velocity was displacement over time, then we have here the equivalent of it, which is angular position divided by time, right? So time is time, time is time. Now, all that's changing is the numerator here. Instead of your distance that you travel, your displacement, right, your meters, your kilometers, your centimeters, you're going by your radians here, right? So your units here would be radians per second. And now a reminder here for uniform circular motion, your average velocity, right, is equal to your instantaneous. Your average acceleration is equal to instantaneous acceleration for uniform circular motion. You're traveling the exact same like distance over time, right? You're accelerating constant. So once again, we have these notations here for angular velocity. So if you have a positive angular velocity, that just means you're increasing your angle from the positive x-axis upwards in a counterclockwise manner, right? So counterclockwise is positive, clockwise is negative. So if you have a positive angular velocity, it denotes that it's counterclockwise direction. If it's negative, it's clockwise direction, right? And so just the value alone for angular velocity just indicates how fast the object is rotating about the pivot, right? In a sense of how much of an angle am I covering per second, right? That's the idea, how to think about angular velocity. How much of the angle am I covering per second? How much, like, what is the proportion of the circle essentially that I'm covering per second? As opposed to with regular velocity, right, your translational velocity, that's just like the distance that you cover per second. So the physical distance around the circle that you cover per second, as opposed to like the proportion or the angle that you cover per second. So that's why we use radians per second for angular velocity, meters per second for linear speed, right? V is equal to distance or displacement over time, right? And so just like with displacement, or just like with velocity and speed, right? So for velocity, the absolute value of it is your speed. And so the absolute value of your angular velocity is your angular speed, right? So if it was negative, for example, if it was negative 6 radians per second, well, then the angular speed is just positive 6 radians per second. So you just take the absolute value to get your angular speed. Now, you can see here, and then we'll hint at this later, but for the angular velocity, the radius is irrelevant. And by that I mean anywhere, any point along the circle, right? If I choose here, if I choose there, if I choose here, if I choose here, if I'm there, here, there, right? I'm going to have the same angular velocity everywhere, right? It's not radius dependent. And so that'll come into play here in a sec. But, just to kind of go back here, like the reason why radius is irrelevant is that like, regardless of where I'm at, my angle is the same, right? So if I'm traveling at if I'm covering a certain angle over time, right? I'm covering that same angle, per second. But I could very well be going faster or slower in terms of like my speed, like my translational speed, my linear speed itself. I could be going faster or slower depending on the length of the radius. Where am I along the radius from the pivot or from the central axis? So if I have a smaller radius, right, then I'll have a smaller speed. If I have a larger radius, I'll have a faster speed in terms of v, right? Now, angular velocity, it's not dependent on the radius at all. You just cover the same angle every time interval. But we'll get to that in a sec. Now, this is just kind of another rehash here, and very similar to the uniform circular motion stuff that we did 2 weeks ago, I think now. But with angular speed, it's 2 pi over t, right? T is your period, once again, and that's how long it takes for you to cover one revolution, right? So essentially, for angular speed, if you look at the equation here for angular velocity, right, we have delta theta here, right? That's the your change in your angular position, right? It's going to be the angle that you cover, and it should be in radians. So I can say, for example, I cover 2 pi radians in some time interval, right? And that's how I can get my angular speed. So that also brings us to the fact that 1 over t, 1 over the period, right, is our frequency. So angular speed is also equal to 2 pi times your frequency. And your frequency, remember, is in units of like revolutions per minute, revolutions per second, like that. So if I said I have 7,200 RPM, like in this problem, or there's a later problem, I think, but 7,200 RPM, right? I convert that to RPS, which is revolutions per second, because I want things in seconds always, or almost always, unless they state it explicitly that they want it in minutes in the problem. But revolutions per second, we convert that, we go from minutes to seconds, and then that's going to be our frequency, basically. Because that way, we can then figure out our angular speed. So there's our equations there for angular speed when we have period and frequency and stuff like that. So this is where I was talking about earlier with angular speed, right? So our translation, our linear speed is v is equal to r times the angular velocity, right? So linear speed is dependent on how far you are from the central axis. So if I'm farther away, if this is 3 meters and this is 6 meters, and we know that our angular velocity or our angular speed is not dependent on the radius. So if I cover, let's say, pi over 2 radians every second, right? Pi over 2 radians every second, or just to keep it simple, pi radians per second, right? That's my angular speed, for example. That's constant. Every single place here, I'm going to be traveling pi radians per second, or covering an angle of pi radians, right, every second. Now, depending where I'm at on the radius, if I'm closer to the central axis or if I'm farther away, that'll affect my linear speed. So the farther away I am from the central axis, the greater my radius is, the greater my speed, right? Now, centripetal acceleration, we can also rewrite that, right? Because we know that centripetal acceleration is v squared over r. So v, we know, is equal to r times the angular velocity. So we can just honestly just throw that in, right? R angular velocity, and that whole thing squared divided by r. So that's r squared angular velocity squared divided by r, right? Your r's cancel out here, and you're just left with angular velocity squared times the radius, right? So that makes sense. So here, a bigger radius means bigger speed. Bigger radius means bigger linear or translational speed for a fixed angular speed. You have a fixed angular speed. The farther away you are from the central axis, the greater your radius, the greater your linear speed. But yeah, and this is just another reiteration, right? The way I like to think about it is, once again, speed, right? Your translation, your linear speed is kind of basically just how much like distance you're covering per second, right? How far or how much distance you're traveling per second. I'm covering 3 meters per second, 30 miles per hour, whatever it is, right? As opposed to the angular velocity or the angular speed, that's like how much of an angle, or what's the proportion of the circle that I'm covering per second, right? I could be covering 2 pi radians per second. I could be covering pi over 6 radians per second. I could be covering pi radians per second. That's my angular velocity. So think angles, radians, degrees, speed, meters, kilometers, centimeters per second, right? That's the idea. And so, yeah, this is just a rehash from last week as well. We know that 2 pi r over t is equal to v, and that's equal to 2 pi rf as well. Now here's where we get to the torque stuff. So we know rigid body is an extended object. The size and shape doesn't change as it moves, right? So a rigid body is an example of like a wheel or a tire, right, or something like that, where you have this central axis here, that's your axis of rotation, and it's not like a localized, just a central object, right, that necessarily the axis is doing the motion itself. It's an extended object. It has these spokes, right? It has extensions of itself, essentially. Size and shape of the overall object doesn't change, but everything kind of moves together. And that's why, it's another reason as to why your angular velocity is constant everywhere, is that you're covering the same kind of proportion of the circle, or you're traveling the same angle over a specific time interval, right? And the whole thing kind of moves together. But yeah, and sometimes we call the axis of rotation the pivot, and we'll hear that a lot here in a sec. So translational motion, obviously, that's just literally just traveling over kind of a linear distance, or just solely just moving the object along. Rotational motion, you're actually rotating the object itself, right? But if you throw something that is an extended object, for example, you're bound to see it have both translational motion, where it's literally just moving over the x-axis or over the y-axis, for example, but also the object itself is rotating as you go along, right? And this is what I was talking about earlier. Every point on a rotating rigid body has the same angular velocity, right? So once again, this is our indication of linear speed. Linear speed will be different at different points along the circle based on how far you are from the central axis, but your angular velocity will stay constant, right? It's equal over the entire circle, basically. Every single point, it's equal. But yeah. Let me skip over these for a second. This is just more examples. Really, this is not super like necessary, but the non-uniform rotational motion stuff, because you're almost always going to deal in uniform motion, but it might be a tested concept in the sense that you might get an indication of like angular acceleration. I'm not sure if they went over this. These are my old slides, by the way, just to let you guys know. But for average angular velocity, right, when you have non-uniform motion, your instantaneous angular velocity isn't always the same throughout. So when you have uniform circular motion, your instantaneous angular velocity is equal to your average angular velocity, right? So the average angular velocity over time is equal to the instantaneous. So like if I take the angular velocity at any single time interval, right, it's going to be equal to the average. And that's the same for like uniform linear motion, right? In the first couple of weeks, our average speed is equal to our instantaneous speed. So at every single time interval, our speed is the same, or our velocity is the same, right, as the average velocity over the entire interval, right? So when your average is equal to your instantaneous, that's when you're uniform. Otherwise, you're non-uniform. And so with your average, once again, you can figure out by looking at the change in the angular position over a certain time period, right? Now, for angular acceleration, once again, that's kind of a throwback to just regular acceleration, because remember, regular acceleration was velocity over time. So our equivalent for velocity in rotational motion, the equivalent is angular velocity, right? So velocity, angular velocity for rotational motion, just regular velocity for like linear translational motion, right? So if I want to get angular acceleration, average angular acceleration, I take the change in my angular velocity divided by time, right? That makes sense. And so with regards to like signs and stuff for angular acceleration, this is kind of, once again, another throwback to the first couple of weeks, where if I'm traveling, for example, along the positive y-axis, I'm having a positive velocity. If I'm slowing down, anytime I'm slowing down is when I have the velocity and the acceleration don't have equal signs. They're not the same signs. So if I'm slowing down while moving to the right on the positive x-axis, so I have positive velocity, if I'm slowing down, then acceleration is negative. It opposes it. If I'm speeding up along the positive x-axis, moving to the right, but speeding up, it's positive velocity because I'm moving to the right along the positive x-axis. And since I'm speeding up, it's positive acceleration, right? I accelerate forward in that same direction, I speed up, right? Same thing with rotational motion. It's just that you have different variables, right? So I have, for example, positive angular velocity. I can have angular acceleration be negative, for example, if I am slowing down. If I'm speeding up, positive angular velocity, positive angular acceleration, right? The issue here is that you have to remember the notation. So positive is counterclockwise, negative is clockwise. So if I'm moving this way, right, what direction is that? What is my angular velocity in that case? Is it going to be positive or negative? This way is going to be negative. It's counterclockwise, right? So if it's counterclockwise, it should be positive. So your angular velocity is positive. So remember, counterclock is positive. Clockwise is negative, right? Yeah, counterclockwise is positive. So if we're moving in a counterclockwise direction, right, then our angular velocity is positive. How about this way? If I'm moving clockwise, what's my angular velocity? Positive or negative? Negative, right? If I'm moving counterclockwise, or if I'm moving clockwise, it's negative angular velocity, right? Now, what if I told you I'm moving counterclockwise and I'm speeding up? Counterclockwise, so we said that counterclockwise is positive angular velocity. What would my angular acceleration be? What's the sign? If I'm speeding up. Positive as well, right? Because when I'm speeding up, the signs for velocity and acceleration have to be the same. If I'm slowing down, they're opposite, right? So if I'm moving counterclockwise indicates that I'm having a positive angular velocity. If I'm speeding up as well, then my angular acceleration is going to be in the same direction, counterclockwise, and that's positive. How about if I'm moving counterclockwise and I'm slowing down? What are my signs for angular velocity and acceleration? If I'm moving counterclockwise and slowing down. Yep, angular velocity is positive because it's counterclockwise, and then acceleration is negative since I'm slowing down. They have to oppose each other, right? So same thing if I go down here, right? If I move this way and I am speeding up, what are my signs for angular velocity and acceleration if I'm moving this way? Yep, so both are negative, right? I'm moving clockwise, so that's negative angular velocity, and I'm speeding up, so it should be the same direction for angular acceleration, so both are negative in that case. So negative angular velocity, negative angular acceleration when I'm moving this way. I'm moving clockwise, so that's negative motion, that's negative angular velocity, and I'm speeding up, so my angular acceleration has to have the same direction, so negative acceleration. So hopefully you get the gist of that. But yeah. This, I'm not sure if they, did they review this stuff? Because this isn't, once again, this is an old lecture, and like I said, they covered some things that you guys didn't, like the moment of inertia stuff. Is this familiar at all? Okay, cool. I'll skip it. Okay, now we're coming to torque, right? So torque is where things get interesting. So just think of torque as kind of the force's ability, or a force's ability to cause rotation in an object. Torque is just a force's ability to cause a rotation in an object, right? So torque depends on the force, right? If we're exerting a lot of force, we're probably going to be exerting or, causing a greater torque, right? And then the object will have a greater ability to rotate. Now, at the same time, it also depends on distance from the pivot, right? So if I push farther away from the pivot, then I have a greater torque. And then therefore, greater torque just means a greater ability to rotate the object. So if I push farther away from the pivot, it just makes it easier for me to rotate the object. So if I think of opening a door, right? Opening or closing a door. So literally, if you want, just to go try it and, have it relate to, the physics concept and try it in the real world, you can literally just go to your door right now. Like if you're in your room, just go to your door and then open it and close it basically, right? Or open it first and then try pushing at different locations on the door. If you push straight on the hinge or on the pivot, literally just put your finger right there, which is dangerous, but for the sake of physics, we'll try it. So if you push on the pivot, right, push on the hinge, nothing's going to happen, right? Or it's going to be really tough for you, for example, to have that door rotate in any way. And so if I start exerting a force farther and farther away from the hinge or the pivot on that door, it's going to be a little bit easier to push the door open or close it, right? So if I push 3 centimeters or 4 centimeters away from the hinge, right, it's going to be a little bit difficult because I'll have a very small radius, or very small distance away from the pivot. And so if I want to exert a torque, right, if I want to increase the ability of the object to rotate, basically, then I have to exert a really huge force to allow the door to close or enable the door to close, right? As opposed to if I were to really have a great radius, right, if I push near the doorknob, right, well, there's a huge radius because it's way far away from the hinge, right? So if I have a huge radius, then I can exert less force in order to have the same torque or the same rotation, or enable the same ability for that object to rotate. So let's say the object, for example, needs a torque of 100 Newton meters to be able to properly open or close, right? So there's a couple different options to do that, right? Now, if I were to push, for example, let's say 2 centimeters away, this isn't really proper, I guess, because of the Newton meters. Let's say if it was Newton centimeters, which is ridiculous, and this isn't. I'm just going by values to kind of explain what's going on in a sense. So if it's 2 centimeters, if I'm pushing 2 centimeters away from the hinge, right, that's pretty close to the hinge. And so in order to have a torque of 100 newtons, I'd have to exert a 50 Newton force, for example. And that's assuming that the third component of torque, which is the angle at which you apply the force, is just 90 degrees. If sine of 90 degrees, sine of 90 degrees is just 1. So I would need to exert a 50 Newton force 2 centimeters away from the hinge. That's pretty close. Need to exert a really great force to be able to open that door, rotate it to where it closes, right? Now, what if I push 10 centimeters away, right, at that same 90 degree angle? Well, then I only have to put in 10 newtons of force. Big difference, right? So I don't have to put in a lot of force to enable the object to rotate and get that torque of 100 Newton centimeters, right? Or 100 Newton meters or whatever. So the idea here is there's 3 components that torque will depend on, right? And so that's the magnitude of the force, right? How much force you're exerting to enable that rotation, how far away you're exerting that force from the pivot or the hinge, and then the angle at which you apply it, right? So if I, let's say, instead have a smaller angle, right? The smaller the angle that I have from 90 degrees, that is. So if I go from 90 degrees to 80 degrees to 60 degrees, my sine value then will be smaller, right? So if I have a smaller like sine value, sine phi, then I might need to, for instance, like exert a greater force, right? So if I applied a force, once again, like 2 centimeters away, instead of sine 90, if it was sine 60, for example, right? Sine 60 degrees. And I still want a torque of 100. Well, instead of exerting 50 times 2 for sine of 90, right? Remember, for sine of 90, we said 50 times 2, for example, to get 100. Then I might need to exert a larger force, because this sine 60 is no longer equal to 1. It might be equal to, I'm not good with the unit circle. I don't know. It's been a while since I've done that stuff. So let's say it's equal to 1/2 or something, right? Then this is 2 times 1/2, right? It's just 1. So in that case, I'd have to apply a force of 100 newtons, so double, right? So there's 3 components, once again, that will affect your torque. Magnitude of the force, how much force you're exerting, right? How far away you're exerting that force, and the angle at which you're exerting, right? So say for example, like I could very well be pushing on the door at a distance 10 centimeters away, right? Or let's in reality, right? Let's say if it was let me look at my door real quick. What's the distance? Like maybe 2 feet, 3 feet. I don't know. So like, let's say 180 centimeters or something like that, right? If it was 180 centimeters, then I can just think of this as that's my total distance, right? That's my total width of the door, for example. If I want to apply a force pretty much at the edge of the door, right, to exert a torque, I don't know, let's say 1800 Newton centimeters or whatever. Once again, I'm just going by values. Then I might need to exert a torque of 10 newtons if it's a sine of 90 degrees, right? Cool. Now, the issue is, what if I applied it, what if I'm just stupid and I decide to push on the door, like literally along the hinge, for example. So at a 180 degree angle or at a 0 degree angle, right? So I'm literally just like pushing on the I guess, like if the door's like this, right? And here's the hinge, and I'm pushing literally this way. Like here's the doorknob. So instead of pushing like open the door or closing the door right normally like a normal person does, I push literally like along the hinge or the radial line instead of perpendicular to it. So that would give me an angle of 180 or 0, right? Well then, since it's on the radial line, sine 180 or sine 0 is just 0. So it pretty much eliminates any ability for that thing to rotate, right? And that makes sense. If you so happen to be that curious or quirky to open that door in that way, then you can very easily see that it's damn near impossible to do that. You would have to apply it at a different angle. You apply that force at a different angle to enable the door to rotate. So yeah, the R always has to be in meters. I'm just going by like, I'm just trying to give simple values and stuff. But yeah, it's always Newton meters. Like, so forget the centimeter stuff that I was talking about. I'm just going by like values that there's, I don't know, just looking at more realistic values, because I don't think a door is going to be like 5-6 meters long, right? But yeah, anyway, yeah, torque is in Newton meters, so keep it in meters for everything. But with regards to torque as well, you have the radial line and you have a force applied. So when we're considering the angle that we're using for our equation, Fr sine phi, right, is equal to torque. That angle is the angle that's sandwiched in between the radial line and the force. So here's that angle, sandwiched in between, right? Now, that would be like if they told you, for example, if they said the force is applied 30 degrees from the perpendicular, that's not the angle that's sandwiched in between. It has to literally be touching, like the angle here has to be touching the force vector, and it has to be touching the radial line. So you can see here, touches at this point and touches at this point. But if you go by this angle, it only touches the force and it touches the perpendicular. It doesn't touch the radial line. So your angle phi that you use is the one that's always sandwiched in between the radial line and the force that's in question. And yeah, we already kind of went over this. And then once again, positive for counterclockwise, negative for clockwise. And it's Newton meters. So these are just other examples as well. And I guess maybe just for the sake of like explanation for the counterclockwise stuff again. So if I push this way, for example, I'm pushing the door upwards, right? So imagine this whole hinge, or this whole rod here, this whole door will go upwards like this, right? So that's moving in a counterclockwise fashion. So that would exert a positive torque. Once again here, for example, I'm applying the force along the radial line. So the angle phi there is equal to 0. So sine of 0 is just 0, right? Or, for example, if I were literally going to push this way, right, same deal, 0 degrees. So it would be exerting a 0 torque. So you don't have torque applied at the pivot. Torque is 0 at the pivot. And it's also 0 when the theta, or the phi, right, the angle is 0, right? At the pivot, R is equal to 0. That's the reason why torque is equal to 0. You're not applying the force at any distance away from the pivot. Because remember, torque is equal to Fr sine phi. Well, if you're applying it at the pivot, R is equal to 0. So if R is equal to 0, the whole thing goes to 0, right? Same thing for the angle, right? If I'm applying directly along the radial line, so if I look at, remember, the angle is the angle sandwiched in between your force and your radial line. Well, if they're literally on the same plane, there's no angle here, right? I'd have to apply it like this, for example, or I'd get maybe a smaller angle like 30 degrees or something like that. But the more I decrease it, the more I push in a certain way, this goes to like 20, for example, or 10, up until I get to 0. Well, once I get to 0, if I'm pushing directly along the radial line, I don't have any torque applied there, because the angle would then be 0, and so sine of 0 is just 0. So there's two instances where you can have 0 torque, either when you're applying a force at the pivot or you're applying a force along the radial line instead of at an angle. So if I, for example, also push down like this, right, it pushes it clockwise, and clockwise is negative. So that's another way to think about things as well. Now, concept of net torque, it's just really like adding up all the torques that you have, right? So if I have this pivot right here, then I want to look at how the forces that are applied, like what torques are they going to be exerting. So if I pull this way, right, it's going to pull the rod like this, in this direction, right? So it moves it clockwise. Right? Because you're going to be, imagine if you literally like pull it this way. So the whole thing is going to go like this, right? And you can see here, if this was, for example, like a minute arm on a clock, if I pull it this way and it goes like this now, right? Oops. If it goes like this, right, downwards, like that, it's as if fast forward in time. So I went clockwise. So just think of like, okay, if I literally, like if I were to, you can try this out, right? And it's very helpful for the exams and quizzes. If you just grab your pencil and you literally like put your finger, like hold your finger right here at the pivot to keep the pencil steady, for example, and then you literally just pull the pencil in the direction of that force, you can see then, okay, like think of the entire pencil as a minute hand on a clock, right? If I pull it like this, oh, I can see that the minute hand went forward in time. So it's clockwise if I pull in that direction, right? So I can literally just hold my fingers here at the pivot. So if this was my pencil, if that was my pencil, right, then I can hold it right here. I can hold my fingers right here at this point, this pivot, and then pull with my other hand in this direction. And then I can see what happens, right? I can see that, okay, well, if I pull in this way, the whole pencil is going to go this way, as if fast forwarding in time, going clockwise, right? Same thing for here. I can pull this way, right? And I can see that moves counterclockwise. Counterclockwise is positive, clockwise is negative, right? And so when you're calculating net torque, right? So I have net torque. I can integrate my signs for torque immediately, right? So if I know that this 8 Newton force is clockwise, right? So it would be negative. So negative torque for the 50 Newton force, right? And then this force, this 10 Newton force, is pulling it counterclockwise, which is positive. So there's a positive torque for the 10 Newton force, right? So I can write it like that, for example, to figure out my net torque. Now, for each individual torque, once again, you can calculate it by F R sine phi, right? So here's your force, 8 newtons. R is the distance away from the pivot, So if this is the pivot, 25 centimeters is going to be the radius for this 8 Newton force, and then 75 centimeters is going to be the radius for this 10 Newton force, right? Force is 10 newtons, force is 8 newtons, and then your angle here, your phi, right, is going to be dependent on the angle that is sandwiched in between the force and the radial line. So would we use 50 degrees here? Why is that? Exactly, right? So we use 40, right? Because this is, once again, this is going to be the angle from the perpendicular, which is not what we want, right? Because you can see if this is our radial line, right? Here's the force, here's the angle. It's not touching the radial line. It's only touching the force. So we want this angle here that's going to be touching the radial line and touching the force, right? So if this is a 90-degree angle, then if this is 50, the other one is going to be 40. This one, however, we can use the 30-degree angle because you can see the radial line is here. Here's the angle. It's sandwiched in between the radial line and the force. Like this. Yeah, they should all be kind of like this same setup, basically. And yeah, you'll always be able to kind of draw the radial line there. And in the event that you don't quite see the radial line and what's going on, right? For example, like this problem right here, which is literally just a circle without any indication, right, of where the radial line is, we'll just think of radial being radius, right? So if this is my central axis, right, for a circle, central axis in the middle. So if this is where my pivot is at, the central axis, the radial line always has to intersect or cross with the force that you're looking at. So if I'm exerting a force at point P, then I have to draw a radius basically that intersects with that force. So it would literally be like this. Or if the force is here, for example, it'll be like this, right? That's how I would draw my radial line. In the event that it's not given. Yep. But generally it'll be this setup, and they very, very rarely, if ever, will they kind of do the perpendicular stuff, because it's not necessary really. It's just, they should just test you on the idea of getting this angle in here in between, but still be prepared for this idea here where you have to get the complementary angle, which is 40 degrees, because it's the angle between the force and the radial line. Now, this is a really important problem. It's just merely conceptual, honestly, because here, right, if we have a force applied at point P, right, we want to see, and we also have a force here as well, right? We have a force here. So we want to see what force applied at point P will cancel out and make the net torque 0. So question, is this force that's being exerted at the pivot, is it exerting a torque? Why is that? Exactly, right? So you're applying directly at the pivot, so R is equal to 0. So this doesn't even factor in terms of the torque itself, right? But it still factors in terms of force. So if we were trying to find the net force, and this was static equilibrium, right? Static equilibrium is when net force is 0 and torque is 0. So if we were trying to figure out the net force and stuff, this for sure has a y component and it has an x component to its force. But in terms of net torque, we don't factor this in because it has a radius of 0, right? So literally we just have this force here that's small like this, right? That's going to be pushing, right, this wheel in a counterclockwise positive direction, right? So at point P, I'd have to exert some force to be in the opposite direction, first of all, right? So if this is counterclockwise, if this is pushing to the right and eventually move up, right? So counterclockwise is positive. Then at point P, it only makes sense for the force to be pushing in what direction? Clockwise, right? Now we can go ahead and look at these and eliminate some options, right? So if I push like this, first of all, D. Let's look at that one for a sec. If I push like this, is this actually applying a torque at all? No, excellent. Why? Yep, exactly, right? So if I were to draw, once again, draw my radius, right? Because this force is in question, so I have to draw my radial line intersecting with the force. If the force is directed like this, well, you can see it's directed along the radial line. So the angle phi is equal to 0. So if I calculate torque, F R sine phi, if phi is 0, then torque is 0, right? So D is not an option at all, not for the sake of like it being a large or a small force or being counterclockwise or clockwise. It literally doesn't even factor in the force or a factor in the torque, right? Because it's directed along the radial line, right? Now, with D being eliminated, we have A, C, B, and E, right? That will actually give us a torque, right? That we can look at. Now, we already said that we want to make the force be applied like or cause a torque in a clockwise direction, right? So if this was going counterclockwise like this, we want to make the force at point P move in a clockwise direction. So how about C? C, if we go like this, is it going to be is it going to be clockwise or counterclockwise? Clockwise, right? So if I push upwards like this, kind of like that, right? It helps the wheel kind of move along in this direction. It's clockwise. So C might be viable. How about E? If I push downwards like this. If I push downwards like this, is it clockwise or counterclockwise? Counter, right? If I push downwards like this, it pushes the entire wheel this way, so it's counterclockwise. So we don't want E, and we don't want D. D didn't even exert a torque. E is actually in the counterclockwise direction. So all that's left now is A, B, and C. So B, if we apply a torque like this, or a force like this, right, is going to be counterclockwise or clockwise? Counterclockwise, right? If we're pushing this way, pushes the entire wheel like this. So it's counterclockwise. So we can eliminate B as well. So we're left with A or C. Well, they're both applying a clockwise direction, which is what we want. It's just that there's a difference in the magnitude of the force. Well, how do we know if it's this one or this one? Well, you look at what are the components that are affecting torque. We know that there's a force, there's a radius, and there's a sine, right? Both of these are directed along which angle? If it's just literally like this or this, what angle is that? 90 degrees, right? Straight up, just perpendicular along the radial line. So the angle doesn't factor in. Well, what else? The force is clearly different, right? There's a difference in force. But why is there a difference in force? Like, how do we determine if we use the bigger force or we use the smaller force to cancel out this torque right here? How do we determine? The radius, right? Because this force right here is exerted, let's say if this whole thing, the whole radius was 4 meters, right? This force right here is exerting a torque 4 meters away. This might only be 2 meters, right? So if I want to, if let's say if this torque was a total of 20 Newton meters, right? And we know that the angle is 90 degrees. Well, if this is 4 meters away, and FR sine phi, right? And sine 90 is 1, right? So if the force was, let's say, 10 newtons, right? Times 4 meters away, that's 40 newtons, right? Newton meters, sorry, yeah, 40 Newton meters for the torque. And that's counterclockwise, so that's positive. Now, if we want to apply a force here that would cancel this one out, right, in the clockwise direction, then we have to exert a larger force to make up for that smaller radius. So if the smaller radius is like 2 meters, right, if we want to have that same 40 Newton meter torque, but be negative essentially, right, then we have 2 meters, right, then we need to apply a 20 Newton force. 20 Newton force to get 40 Newton meters, and then that's going to be in the negative direction, which is clockwise, right? So you can see here that it would have to be A because it's almost like double, if not more, than the size of this force right here. So it has to be A because it's a factor of the different radii. This is at the maximum radius, this is only about halfway. So you have to exert a larger force because of that smaller distance. So it's like pushing on that door once again. If I push closer to the doorknob, I don't have to exert a lot of force to open and close the door. If I push closer to the hinge, for example, right, closer to the pivot, like this one, closer to the pivot, then I have to exert a larger force to get that door moving, right? This is once again just kind of net torque, right? So by now, I think you guys should understand like the concepts of how to like do the net torque stuff, especially now that I've explained directions and all that. And it's very similar to calculating like net force and stuff. And let me look, what else is there left? I think just center of mass, honestly. I want to look here real quick. Yeah, I think it's probably just center of mass that's left. For center of mass, it's just kind of like the average, the weighted average, right, of the mass of the object, basically, right? Your center of gravity won't necessarily always be in the center if it's not a uniform object. It might be shifted a little bit to the right or a little bit to the left or something right like that, right? It just depends on the weighted average for the mass of the object, right? So for a uniform object though, center of mass is just the geometric center. So if they said like a uniform beam and it's 5 meters in length, right? 5 meters in length for a uniform beam, then you know the center of mass or the center of gravity is going to be at 2.5 meters. If it's 6-meter beam, that's uniform. Uniform just means that just the same density all throughout, right? And so that means at that point, if the beam is 6 meters, then the center of mass or center of gravity is at 3 meters, right? Now, center of mass equation, you can see is kind of like that weighted average that I was talking about. Weighted average of the different pieces, right, of an object, basically. So if you have like a hammer, right, we have the hammer head itself and you have like the handle. So those will have like their own kind of individual masses. So like you calculate kind of like the mass of the handle and the mass of the hammer, right? Do the weighted average of the masses, and then that's how you can get like where the center of mass is exactly located, right? So the way you do that is you take the mass of the first object, for example, times the distance away from the pivot, right? And then add it up to the mass of the second object times the distance away from the pivot, etc., 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 and then divided by the total mass of all the different pieces in the system. And that's for center of mass in the x direction and center of mass in the y direction. So if I want to figure out center mass of this system right here, I take the mass of this object, right, times its distance away from the center, or the pivot, right? So if I want to make this the pivot, then it's 0 meters away. If I make this the pivot, it's 0 meters away for that mass. So just basically, if you have, for example, 1 meter long dumbbell, so this whole thing is 1 meter, right? That if I make this my pivot, then my x distance for this mass is 0, but the x distance for this mass is 1 meter, right? It's the whole dumbbell length. Now, if I were doing the center of mass for that one, it'd literally just be what you see here. It'd be 0, right? 0 meters away times the mass of the first object, which was what? 8 kilograms, right? So 0 meters times 8 kilograms plus 2 kilograms, which is the object on the right, times the 1 meter distance away, and then divided by the total mass of the system, which is 10 kilograms, right? That's how you would get the center of mass in that case. Center of mass is generally pretty easy. It isn't a horribly difficult concept as compared to torque, especially. But for this, right, you do the kind of the same deal. It's just that I would break things up into like an x center of mass and a y center of mass. So like here, like you have your x-axis essentially, right, and you have your y-axis. So I'd find the center of mass along the x-axis and the center of mass along the y-axis. So like if you had this whole like boomerang shaped rod, right, this L-shaped piece, then these are kind of like your two pieces, right? These are your two pieces here, these two like trapezoids essentially. They'll have their own kind of masses. So if you take like the mass, and it actually it wouldn't even be their own masses. I made that mistake. So it's not actually even their own masses because it's going to be the same mass, B and D here, right? Because it's B and D will be just the overall mass for that object because both points are along the object, so the mass is the same. So if the mass is the same, right, it's m1x1 plus m2x2, right, divided by m1 plus m2. If m1 is equal to m2, then it's also kind of like writing m1x1 plus m1x2, right, divided by just m1, right? And so you can see that the m's will basically cancel out in a sense, and you're left with more or less a just an average of the distances away. But I don't like doing it in that way. I like to be a little bit more thorough so I can visualize what's going on. So I can just think of like x and y center of masses. So if I make this kind of like my axis, my origin, right, B is a certain distance away and D is a certain distance away, right? And those are both points on the actual like rod itself or the L-shaped piece, right? So if this is like 3 meters away and this is like 9 meters away, right, then the average in between them, 3 plus 9 is 12 divided by 2, right, for the two masses. is just going to be 6 meters. So somewhere along the middle here, in the x-axis at least, is where my center of mass should be. That's my x-coordinate for the center of mass. Now, for the y component of the center of mass, if this was, let's say, 5 meters upwards from the bottom here, and d is 10 meters upwards, right? Then 10 plus 15 and divided by 2, or 10 plus 5 divided by 2, 15 divided by 2, so that's 7.5. So you can see that it's about at point A, for example. This one? Yeah, just because we're only interested in the x-axis. Yeah, so y-axis isn't relevant in this case. Mm-hmm. Yeah, kind of, yeah. Yeah, so I just choose like an arbitrary like origin point. So I just pick like right here, right? This is my origin point. So along this axis right here is the x, along this axis is the y, right? So if I want to look at the x, like the x component of the center of mass, right? Then I look at things along this axis right here. So I choose like this is, right, a point on the actual like piece itself, and this is a point on the piece itself, right? They'll have the same masses. And so since there's the same mass and stuff, I don't really have to worry about the mass in that point. So I would literally just take the average position basically between these two points because they're the same. They're located on the masses itself. So it's just a matter of taking the average position or average distance in between these 2 points because they're located on the mass itself. So if this was, let's say, on the x-axis like 3 meters away or something, right? And this was like, this is 9 meters away, right? Then, and this is like that, right? So I do 9 plus 12, damn it, 9 plus 3 meters, right? That's 12 meters, and then divided by 2, that's like two points, right? Those are 2 values that you're calculating. That gives you a average of 6 meters, which is right in the middle. And then you do the same thing for y, right? If you're on the y-axis, x-axis here, then I look at how far this is upwards. This might be like 5 meters. How far this is upwards. This is 10 meters. I add them together, 10 plus 5 divided by 2. 15 divided by 2 is 7.5 meters. So that's like the average distance, right, between them along the y-axis. So the point should be like 7.5 meters, which is in the middle between 5 and 10. Cool. But yeah, this is kind of a conceptual type problem. I don't foresee them like doing this for like a written part, but just so you know, keep it in mind. And gravitational torque is just like torque just with the force of gravity basically, and we're going to do a couple of examples of that later. But I just want to get to this torque with the alternate ways of finding out torque isn't too bad, so I'll skip this part. And then we're just left with the second part of the center of mass stuff, which is more conceptual, and that's just like the idea of base of support. And I'll just like very briefly go over this so we can get to the problems. The idea of base of support is like thinking of the platform that the object is kind of resting on. So if you have like a car, right, your base of support is just the distance between the 2 tires, right? That's your base of support. It's like what the car is kind of resting on. And then the idea here is that center of gravity of the system, if the center of gravity of the system is located within that base of support, so like if you tip over, right, if you get in an accident or something, you kind of tip over the car this way. If the center of gravity of the system or the center of gravity of the car still lies within that original base of support, right? So let's say the distance between the tires here is like 2 meters or something, right? If it's 2 meters, then here's my original base of support, 2 meters. If I start tipping over due to an accident or something, or if I swerve, then my center of gravity, when I swerve, right, I kind of move to the left a bit. I tilt it to the left. So it's going to shift over from its original position. It'll shift over to the left or to the right a bit, right? So Thing is, it's still within the base of support. It's still within that 2 meters. So maybe initially it was right smack dab in the middle at 1 meter, and now it might be like 1.7 or something. As long as it's within that 0 to 2 meter range, basically, the car is going to move back in its original position and stay stable, basically, right? Now, if I tip over a bunch and my center of gravity of the system is directly like over that limit for the base of support, so this was 0 to 2 meters, right? If I tip over a lot where now my center of gravity is located, shifted over rightwards even more, and now it's located directly over the 2 meter point, then any additional like force or tipping over from the car is going to cause me to just, like you see here, it goes past the base of support. So this was 2 meters. Maybe now if I tip a little bit more, I'm at 2.5 meters or something, right? So then once it's outside the base of support, that's where the object starts to tip over. So base of support is like your platform that the object is resting on. If the center of gravity is within that base of support, then the object remains stable. Once the center of gravity is directly over it, that's its maximum point. If I tip any farther or go any farther, like on a plank or something right here, right? If the cat walks any further past its base of support, then the center of gravity will change, and then the plank will tip over, for example. That's the idea here with base of support, and that's a very, very important concept, and we'll go over that here in a sec. But the idea here is that you're looking at the center of gravity of the system and how it compares to the base of support. So if the cat has a certain mass, a certain force of gravity, and the plank, the beam, has a certain force of gravity, I find the center of mass in between, or center mass of the whole system. So XCM, I take mass of the cat times the distance away the cat is, right? And then plus the mass of the beam, distance of the beam, and then divide the whole thing by mass of the cat plus mass of the beam. That gives me my center of gravity, right, of the cat and plank system, for example. Now, if the cat were to walk further away, then the x-cat increases. If the x-cat increases, the numerator increases. If the numerator increases, then your XCM goes up. So center of mass goes up. So if the cat walks further, the cat moves over here, then the center of mass, right, might shift over like this way. If it walks even further, right, it might shift over here, right, up until a point where the center of mass of the whole system is right there at the edge of the base of support. And the base of support is literally just here to here. It's the area or the section of the plank that's in contact still with like the surface here. If the cat were to go any farther from this position, then the center of mass changes, shifts a little bit more to the right. It's past the base of support. It's no longer over like this section right here, right? No longer from here to here. So the center of mass is here, for example, and then it's outside of the base of support. So then that's when the plank will start to tip. So that's the concept of base of support there. So with that being said, we can move on to the quiz examples here. So I will switch to this one right here. So there's 3 quiz problems that I have. So it's quiz 6 and quiz 7. Like I said, we had torque and stuff and moment of inertia broken up into 2 different weeks. And you see this moment of inertia stuff was really bogus. Like, if you guys don't have any of this, you don't take any of this semester. Take any of this stuff this semester. So you don't factor in like angular acceleration with moment of inertia, and you have all these different values for rods and particles and stuff. It's just very difficult. Or I mean, it's not like difficult. It's just that it's just an extra week's worth of concepts that's just going to overwhelm people on the exam. So it's good that they took it out. So we're not doing this problem, and you guys are not going to have any concepts or lecture about it. And this is the center of mass problem that I was talking about earlier, so we can do that as well. Actually, I might as well do the center of mass one first, because I kind of might have rushed through the center of mass stuff here. So I'll kind of go over this one first to kind of reinforce what's going on. So for this problem, it says, block on a plank, a 2 meter long uniform plank is held balanced on a support. And on the top of the plank, a 1 meter wide uniform block is placed as shown in the figure. The plank has a mass of 4 kilograms, right? So the plank there, mass of 4 kilograms. And the, oh, my bad. This is not the plank. Plank is 4 kilograms, and the block has a mass of 15 kilograms, right? For this problem, take x equals 0 at the left end of the plank. So this is x equals 0 right here, right? So 2 meter long uniform plank balanced on a support, and on top of the plank, 1 meter wide uniform block, right? So now they want us to figure out what are the x coordinates of the center of masses of the plank, xp, and of the block, respectively. All right? So for the plank, we want to find out the center of mass of the plank. So we look back to the problem, right? We know that from 0 up until the end of the plank, it's 2 meters. Now, what's the hint here? They said it's a uniform plank. What does that mean? Yeah, exactly, right? So if it's a uniform plank, uniform beam, uniform density, the center of mass will be in the geometric center. So if this whole thing is 2 meters long, right, the plank is 2 meters long, then your center of mass would simply just be 1 meter for the plank, smack dab in the middle, right? Now for the block, center of mass for the block, well, is the block uniform as well? Yeah, it's a uniform block. So we go start from here, this is 0 meters, and then this block right here is 1 meter, right? Just the block here would be 1 meter. So if this is 1 meter, this distance from here to here, that's 1 meter, right? So this is 0. Up here is then 1, right? And here's 2. That makes sense, right? Because if this whole thing is 1 meter, then this section here as well, this imaginary section here, right, here's another meter. So from here to here, it should be 1 meter as well for this section. So I know that 1 meter's at the beginning of the block here, and then this is 2 meters at the end of the block. So what do you think the center of mass of the block is going to be? And remember, we have to calculate the center of mass relative to this starting point right here, x equals 0 at the left end of the plank. $1.5, excellent, right? So we know that from here to here, it's 1 meter. And then since it's a uniform block, right, then if the block is a meter long, right, then the center of mass is just going to be in the geometric center, so half a meter, basically. Half a meter along the length of the block itself. So 0.5 meters along the length of the block itself. So from here to here, it's 0.5. Well, if from 0 to 1, it's 1, then from 1 and an additional 0.5 to get to the center of mass of the block, well, that's a 1.5 meter center of mass. Does that make sense? Yeah, if you want to plug into the formula, let's see here. So if we do center of mass of the block, right? Let's see here. So it would just be... I'm wondering. Okay. Well, the formula would factor in like both systems, or the overall system. So it would factor in both masses of the plank and the block. Now, if we were just doing the mass of the block, so that's mass of the block is what? 15 kilograms? Times its position away. No, actually, hold up. No, we can't do that. We can't use this equation at all. Yeah, we can't use this equation at all. Because the reason why is that for that center of mass equation, it's factoring in the masses that are included in the system, and then their center of masses in the system, right? So if we were to do that, it would be, oops, it's a huge pen right there. It'd be like x cm mass of the Planck times the center of mass of the Planck plus mass of the block times the center of mass of the block divided by mass of the Planck plus mass of the block. That would get us the center of mass of the entire system. So you use this equation when you're finding the mass of an entire, or the center of mass of an entire system. But if you would just want to if you would just want to find the center of mass of an object alone, right? Then you would have to look at its position relative to like the starting point right here and find, you know that its center mass is going to be 0.5, right? Because the whole thing, this block here is 1 meter long. So its geometric center is 0.5 meters. But then it's 0.5 meters from this point. So 0.5 meters to the right from this starting position right here. Now, this position relative to the 0 point that we indicated is 1 meter away. So 1 meter and then an additional 0.5 to get 1.5 meters. Otherwise, I don't think there's a way that you can use the equation to calculate the center of mass of that one just alone. Well, the XB, the block would be 1.5, yes, but the center of mass for the Planck would just be 1 meter, because it's the center of mass of the Planck itself, so the XP would be 1 meter. And that's actually what we're going to do for part B. So already kind of done what's the X coordinate of the center of mass of the combined block / Planck system. So we literally just take X center of mass. We have the mass of the Planck, that was 4 kilograms, and the center of mass of the Planck was 1 meter away, and then 15 kilograms for the mass of the block, and that was 1.5 meters away, and then divided by 19 kilograms, which is the total mass, and that should give us 1.4 meters for the center of mass for the entire system. But yeah. Does that make sense so far? Okay, cool. For part C, it says if the distance d is equal to 1.1 meters, then will the block / beam system rotate when released? And if so, will it rotate clockwise or counterclockwise? So D, this distance right here, they're talking about from the starting point to the base, to the pivot right here is 1.1 meters, right? Then if we take that support as being the pivot, then we just have the only torque in question that would rotate the object or the system clockwise or counterclockwise. So if we have this is our pivot right here, we know that this pivot right here normally, like it would exert a normal force on the system, right? But if we make this a pivot, then R is equal to 0 for that normal force, and so it exerts 0 torque. So in that case, the only torque that we would have is due to the center of mass or the center of gravity, right, of the whole system. So we know that the center of mass here of the system is 1.4 meters. So that's That's the center of mass of the whole system. So that's where your center of gravity of the system would be located, basically. So if this is 1.1 meters, this point right here, and your center of mass of the system is 1.4 meters, so gravity of the whole system is right here, right? Then basically we have to identify, is the block going to rotate at all? Or, so yeah, does it rotate at all? And if it does rotate, is it counterclockwise or clockwise? So with regard to this pivot here, we can think about the pivot as what? Because this is like just standing in the air right here. It's not connected. This is just a zero, like an arbitrary reference 0 point. The pivot here acts as our what? What does the pivot act as? So like, I guess, when do you think the system wouldn't rotate? When would it not rotate? Any ideas? Excellent, right? Now, when we say that, when the pivot is at the center, or more, actually kind of the other way around, when the center of gravity is at the pivot, that's when there would be no rotation. Why is that? Why do you think that is? What would the pivot kind of indicate or act as? That's what I'm getting at. So like, yeah, so for your first, for the center of gravity, right? If it were right above this pivot, there would be no rotation, like Christian said, right? If the center of gravity of the system is at the pivot at 1.1 meters, there would be no rotation, right? Now, the pivot is not like a contact force. It acts as our base of support, right? The pivot is our base of support. If my force of gravity, or if my center of gravity or my center of mass is located right above that base of support at that 1.1 meter point, then I'm not tipping over, right? So imagine like a teeter-totter or seesaw, right? If it's like this, if you have two people, one standing here, or one sitting here, one sitting here, right? If their combined center of mass is located at the pivot, they will perfectly balance the teeter-totter, right? Now, if one person, for example, is significantly heavier than the other and is causing an overall center of mass to be somewhere here, for example, relative to the pivot, well then, if your pivot is the base of support, then the center of mass is to the left of it. So you'll see it tip over. Just like that car example, right? For the car, you can imagine that our pivot is like right here, right? This is our pivot. This is our support. Let's say it's 2 meters, right? Right here. If it's directly over that 2 meter point, directly above it, we're good. I mean, not really, because you're about to die, but you're still living. Now, as soon as it tips over, beyond that pivot, beyond that support, beyond that 2 meter point, comes 2.5, even 2.0001, it's over with. You're dead. Right? So you have 1.1 meter here. If my center of mass is at 1.4 meters, okay, then that means this thing is going to tip over and going to be like this. Right? Now, if it tips over this way, what direction is that? Clockwise, right? So, yeah, excellent. It would be moving clockwise. And then your explanation would kind of include an idea of the fact that since the center of mass of the system is to the right of the pivot, past the base of support that the pivot provides, then the overall object we pull down and to the right, basically, which is in a clockwise direction, and that would cause a clockwise rotation. Does that make sense for problem 2? Any questions at all about problem 2, or is it making sense? Yep. Hopefully now that kind of clears up the idea of center of mass and base of support. So like if your center of mass of the system is past the base of support, right, then that's when you start to tip over. As long as it's within that range, you're good. So like with this idea of the car, right, if the center of mass, like if you tip over to the left, for example, and it's still within this little range right here, anywhere within this range, right, here, 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 wherever, as long as it's within the range, you're good, you're stable. It's not going to tip over, or at least it's not going to fully tip over, right? It'll stay relatively balanced. If it's directly above, that's its maximum point. If it's directly above that pivot right here, if this was a center of mass like this, then it's getting dangerous, right? Any additional force is going to tip you over. Now, if it's past the base of support like this, you're done for, right? This was 2 meters, 0 to 2 meters right here. If this was 2.1, you're done for, right? Same idea here, and that's what you're gonna see a lot of these examples, maybe either on the exam or maybe on the quiz tomorrow. This idea of base of support with a person or a cat or something like you see here. So here to here, for example, this 3 meter kind of distance is our base of support, right? Here's what's in contact basically. Now, the idea here with like identifying the base of support is that like if that person starts to move more to the right, for example, or if the car starts to move to the left, or to the right, my bad, in that other example right here, then the idea here is that, like, is my center of mass going past my original platform that's giving me contact? So, like, my platform of contact with the car was that my 2 tires, right, keeping me in contact with the ground. Now, the platform of contact here is, like, where the plank, the section of the plank that is in contact with like the ground. So like imagine maybe if this was like a skyscraper or something and there's construction and the cat decides to walk along this plank, for example, or a steel rod or whatever, then the area of that steel rod or the plank, that section right there, that distance that's in contact with the skyscraper is that base of support. Once the center of gravity, which you can calculate using the center of mass equation, right? Once that center of gravity goes past that contact point, right? Once it loses contact with a skyscraper, loses contact with the floor, goes past the support, right? So like we can imagine this is our left pivot or left support. This is our right pivot or right support. If it goes, the center of gravity goes past it, then I tip over. As long as it's here, 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 right above, right? You're playing it dangerous here, but as long as it's within that range, you're good. That's the idea of base of support. But yeah, then we can kind of move on to the actual stuff here for quiz 6. So they made a mistake and put it quiz 5, but yeah, this is quiz 6. This is about the torque stuff. Shoot, I forgot to X out the answers for this one, but it's fine. But for problem 1 here, it says out for a stroll. So it says when a person walks, their leg is effectively a long, straight rod rotating about one of its ends. The hip joint located at the origin in the figure. Treat the leg as a uniform rod of length 0.8 meters and with a mass of 11 kilograms. Now for part A, they say draw an extended free body diagram of the person's leg, labeling the pivot, which is the hip joint, and all forces acting on the leg, even those that which may exert no torque, right? So if you have your leg and you're walking, you can think of your leg kind of as a rod, right? Now, the leg alone has a certain mass, and so therefore it has a center of gravity, right? So if the leg is treated as a long straight rod, right, and it's uniform, what does that mean for the center of gravity if it's a uniform rod? Yeah, exactly. It's in an exact center. So if it's a uniform rod, force of gravity, center of mass is going to be the exact center of it. So this whole thing is like 8 meters, right? Or they said what? It was 0.8 meters, right? then center of gravity or center of mass is 0.4, exactly, smack dab in the middle. Now, force of gravity points straight downwards, right? That makes sense. But our feet are also in contact with the floor, right? So it only makes sense for there to be a normal force acting upwards as well. And then you have to consider, well, okay, if there's a force of gravity and a normal force acting like this, right? Well, I have to look at then, are there any other forces that may exert no torque at all? So, if I'm walking, right? Let me see if I can rationalize this with like centripetal motion, but it might be unnecessary. Do you guys remember when we were talking about centripetal motion, and when you're walking, you kind of feel lighter? You guys remember that at all? Because you remember if you were walking when you're walking, you kind of walk in a circular type motion, and so there's gravity, and you have normal force like this, right? So it's Fn minus Fg, and that's equal to MAC basically, right? So not lighter, my bad. I think it's, in a sense, in that case, would be kind of heavier, right? So Fn would actually kind of be greater than Fg, because Fn minus Fg is equal to MAC. So you can see that Fn is equal to Fg plus the centripetal force, right? In that sense. So that's why you can see here that the normal force is greater, right? The vector is greater than the force of gravity. So if there is that normal force that's greater, there's a force of gravity pointing downwards like this, then it makes sense that we should have a third force to kind of cancel things out, right? That's assuming if we have zero net force, for example, right? But in any case, if we don't know that the net force is 0 or the net torque is 0 or whatever, right? There should naturally, right, based on just biology and stuff, there should be a force that's applied at the hip, right? There should be a force at the hip joint that allows you to even walk from the begin with, right? That makes sense. That's just kind of logical, right? But the thing is here is that when the force is at the pivot, it doesn't exert any torque because R is equal to 0. But it's only logical that there's a force at the pivot because the hip joint will exert a force that helps you walk, right? That makes sense. Now, they ask you what is the torque exerted by the force from the hip on the leg. So this FH, once again, since R is equal to 0, it's acting at the pivot itself. Then torque is equal to FR sine phi. Your R is equal to 0, so your torque becomes 0. So that makes sense there as well. But then you have this part right here is asking, well, if the person is walking steadily, so steadily, there's no net torque, right? Then how does the torque of the normal force exerted by the ground compare to the torque exerted by the weight of the leg, both in terms of magnitude and direction? So first of all, let's start with direction first, right? We want to start out with direction first. What direction is the normal force pointing in this case, right? If we have this pivot right here like this, and it points upwards, is that clockwise or counterclockwise? Counterclockwise, right? So it should be positive. How about force of gravity? Clockwise, right? So there you go. Easy points right there. Normal force torque is positive, right? Because it's counterclockwise. And gravity exerts a negative torque because it's clockwise, right? Now how about the magnitudes, right? They already told us that it's walking steadily, so there's no net torque. So T net is equal to 0. So you have Tn, that's positive, right? Positive torque for the normal force since it's pointing counterclockwise. And then negative torque there for gravity because it's clockwise, and that's equal to 0. So Tn should just equal to Tg, right? There. Does that make sense as well? Any questions about problem 1? Nope. Okay. Now this is the last problem for the quiz. I'm not sure if we can get to the online homework. I was want to, but for some reason these problems take too long, or I'm just too thorough, or I don't know. But if we're not able to get to the or at least some of the online stuff, just meet me tomorrow. I'm at the MSLC. So, but yeah, or just like I said, DM me, and those of you who have been asking me questions, you know that I reply as quickly as I can, and if I can't, then I let you know that I can't reply to you immediately, and I get back to you as soon as I can. And I don't think I've like ghosted anyone, at least I hope not. But anyway, problem 2 is raising a beam. So we have a 6-meter long beam of mass m is equal to 150 kilograms. It's attached to a wall by a hinge, right? So this hinge acts as our what? What does the hinge act as? Pivot, right? Excellent. Pivot. Now, the beam is uniform, so that means that our center of gravity should be in the geometric center of the beam itself, right? And they already tell you that. Gravity is exactly at its geometric center. The rope is attached 2 meters from the end of the beam. So if the whole beam is 6 meters long, where's the rope located? If the whole beam is 6 meters long, where's the rope located? That would be the center of gravity, right? I'm asking about the rope. So if the whole thing is 6 meters long, and the rope is located 2 meters, yeah, exactly, right? So this should be 4 meters away. Yep. And then the rope provides a tension of 2 kilonewtons or 2,000 newtons, and the beam is held at an angle of 30 degrees above the horizontal. That's the beam itself. And then your pivot or axis of rotation should be the hinge, right? So part A is asking us about the torque on the beam due to the tension of the rope. So torque due to the tension, basically. So torque Ft, right? Well, we know that torque is FTR sine of phi, right? So torque is FR sine phi. So we have force of tension that we know, which is 2 kilonewtons, and then its radius away from the hinge, which is 4 meters, and then times the angle that's sandwiched in between the force of tension right here and the radial line, which is that 40 degree angle, right? So it should be 2,000 newtons or 2 kilonewtons times 4 meters away from the hinge, right? That's where the rope is located, times sine of 40, which is the angle sandwiched in between the radial line and the force, touching between those two. And that can give you your torque, right? Now, the tension pulls this way. So should our torque be positive or negative? And why? Why is it positive? Counterclockwise, right? So if this was kind of like a clock, right? Pulls this way, I go backwards in time, counterclockwise, right? For part B, it's asking what is the torque on the beam due to the force of gravity. So it's the torque due to the force of gravity on the beam itself. So we had the mass of the beam is 150 kilograms, and we know that the beam is a uniform rod. So the center of gravity should be smack dab in the middle. So this whole thing is 6 meters. Center of gravity should be 3, right? So then, if we want to figure out force of gravity, or the torque due to gravity, right? We just take force of gravity times the distance away from the hinge, right, along the radial line, times sine phi. Well, if this is our force of gravity here, like this, what is our sine? What is our angle? Excellent. Yep, 100%. This is 90 degrees. 90 plus 30 is 120. So this is 60. Is that how you got it, Matthew? Gotcha, I see. But yeah, this is how you would derive it in general. So like your force of gravity is directed immediately downwards like this. So if it goes immediately downwards, it forms a perpendicular angle here, right? So that's 90 degrees. And so 90 plus 30 is 120. And you know that total for a triangle, total amount of angles, or the sum of the angles, my bad. Sum of the angles on a triangle is 180 degrees. So 90 plus 30 is 120. So this right here should be 60 degrees. And the reason why we use 60 degrees, right? Let me rewrite that here real quick. This is 60 degrees, is because this is the force of gravity. Here's the force. Here's the radial line. It's the angle sandwiched in between. So 60 degrees, right? So we take force of gravity, right? That was 150 kilograms times 10 meters per second squared. That's our force of gravity. Times the distance away, which is 3 meters. And then times sine of 60, right? And that should give us the 3,897 Newton meters. Now, why is it negative? Why is it negative 3,897 Newton meters? It moves clockwise, right? So it pulls it down clockwise. So this is like our minute hand on the clock. If I pull it down, it's going to go this way. Fast forward in time clockwise, right? So the addition of a negative or a positive sign for torque, that's another important concept, isn't dependent on the radius or the sign or the force of gravity itself or the force in general, right? We assign a negative or a positive pretty much like just on our own, depending on the direction. So if it's counterclockwise, it's positive. If it's clockwise, it's negative, right? And so if you're doing your equation, that's what I messed up on the written homework. I made a small mistake of making the force negative. I think I said for that Tom and Jerry question, it was like negative 26.38. It should be positive 26.38. The force isn't what causes or isn't what denotes counterclockwise or clockwise or negative or positive torque. We indicate ourselves if it's negative or positive based on direction. So your direction, like you can calculate everything out, FGR sine theta, or sine phi, right? And then add a negative sign at the end and say like it's negative 3,897, it's clockwise, right? But yeah. And then if you just want to find the net torque, well, look at what forces are there and what is generating torque, right? So there might be a force at the hinge here, right? But since it's at the pivot, R is equal to 0, so torque is equal to 0, right? That makes sense. Now, if we have a force of tension that we calculated, that brings it up counterclockwise. So that's positive. That exerts a torque due to the rope. And then the force of gravity brings it down clockwise. That's exerting a torque as well. That's negative. So those are the only two forces that are exerting torques. And so if we want to figure out the net torque, it should just be the torque due to the force of tension, that's positive because it's counterclockwise, minus the torque due to gravity, and that's clockwise, so it's negative. And so we just take 5,142 and then minus. Now, we know that the torque due to gravity, we said it was negative 3,897, right? That's the torque due to gravity. Now, since I include the direction in my equation from the beginning, I just have to put in the magnitude. So I just put in, what is it? So 3,897, and I calculate this way, right? Alternatively, if you put in plus, well, then you have to indicate the direction. You have to indicate your sign there. But if you put in the minus sign to indicate that it is a negative torque from the beginning, you just plug in magnitudes. So that's how you can get your net torque of 1245 Newton meters. So there's a net torque of 1245 Newton meters, and that's in the positive or counterclockwise direction. So that is all of the quiz problems. Now we have a couple of minutes to do the online stuff. Any specific questions about the online? We have about 7 minutes left, so we might grind out like a problem or two, hopefully. Nope. Nobody have any questions about the online? You guys can hear me, right? I just want to make sure because like last time the Zoom was like mega lagging out. So okay. I mean, it's fine. Like if you guys don't have any questions about the online, you're pretty much free to go. I'm pretty much done with the review for tonight. I don't think there's any additional stuff that I want to go over. We went over torque, we went over center of mass, we did 3 problems for those, and then I did some problems in between here and there with the slides. But for the quiz tomorrow, I would I would make sure to like maybe take a look at the quizzes again that I'm gonna upload those on Google Drive. And then for the slides, really maybe focus on the base of support thing again, because I feel like that would be a good question that they might ask on the quiz, as well as just being more familiar with the notations for torque, right? Positives counterclockwise, clockwise is negative. Positives counterclockwise, clockwise is negative, right? Use your pencil during the quiz, during the exam. Hold the pencil like at a specific pivot, right, with 2 fingers, and then turn it, apply a force that's in the diagram, for example, with your other 2 fingers to kind of see in what direction it's moving, as if you were adjusting a clock, right? That would be the best way to kind of figure things out. Otherwise, center of mass is not too bad. There's a lot of implicit information. So uniform density, whenever you see uniform rod, uniform beam, uniform whatever, it just means that the center of mass is directly in the middle. So if the whole thing is like 10 meters long, center mass is 5 meters for that object, right? Angular velocity, remember angular velocity is going to be the same throughout. It's not dependent on radius. Your linear speed or your translational speed is dependent on radius. So if you go farther out on the circular path, right, if you increase your radius, you're increasing your angular velocity. Or my bad. If you increase your radius, you increase your linear velocity or linear speed, right? So your angular velocity stays constant. It's fixed. Every single point, every radius or distance away from the center axis, right, is going to have the same angular velocity, because angular velocity is kind of a concept where it's like the proportion of the circle, or like the angle that I cover per unit of time, right? As opposed to just regular velocity or regular speed is like the actual distance I cover over a certain period of time. But I think that is it. Just be careful as well with torque. Like if you have a force acting along the radial line itself, sine is 0, torque is 0. If you have a force acting at the pivot, torque is 0. Static equilibrium is when torque is 0, net force is 0, right? Net force is 0, net torque is 0 for static equilibrium. But yeah, honestly, I would just go over the written homework as well again. Make sure to review these quizzes that I'll upload on Google Drive again as well. Go over the slides. There are some excellent problems in the slides. I'll upload my slides as well, so you guys have access to some additional problems from there, and just some of my like explanations or notes on the side about certain topics. And then I think that is it. So I'm at the MSLC tomorrow from 10:15 to 12:15. Stop by if you have any questions, especially for those who are in Ansari's section. I think you guys have your classes in the morning, so just stop by then. Or if you have the Zhong, just I'll hopefully I'm planning on being there until like 2, 3 or something like that. But like officially from 10:15 to 12:15, that's what I'm getting paid for. But then anything else is just, it's almost as if it's just like a study with me hour kind of thing, right? Like I'll just be doing my work, and then if you guys have any questions, like I'll be happy to help on the side. But like the main session, like try if you can to come 10:15 to 12:15. But otherwise, like I'm not gonna ignore you if you come later. But yeah. So I will stop sharing now, and I will end the recording. And good luck tomorrow on the quiz.